So this is one last presentation of mine before I go and give out the real presentation. So I am going to be as humorous and as clear, as evident I can be over there. I can be over there. So mm, let's start. I will just say out my lines. I will just read them out loud. The things I'm going to say over there. So this is the last presentation. Okay, even if I make some kind of mistakes, mm, it is just for practice. So good morning, everyone. Good morning to my respected teachers over here, our respected guest faculty, and my dear juniors and my classmates. So today, my topic for discussion is sedimentology of Mars and the evidence we get from planetary sedimentology, right? So first, let me introduce myself. I am Swastik Chakraborty from fifth semester of this department of geology and of this college. Absolutely. And so most of you are already eager to know what is this guy gonna yammer about? What is he gonna talk about? What kind of things are we getting into in this discussion? So to douse your vexation, I will just share the content with you. So what are the contents of this presentation? Introduction. First of all, I'm gonna introduce you to things like planetary sedimentology and why I'm pursuing planetary sedimentology on Mars. Why not Venus? Right? Why not Venus? Why not Neptune? Why not Jupiter or something like that? Then I will talk about the evidence of sedimentary processes on Mars, whether there are sedimentary processes active there or not, whether there were sedimentary processes active there or not. So I'm going to talk about that. Then I'm going to talk about sedimentary structures, basically miscellaneous sedimentary structures that can be observed on Mars. And after I've done that, I will provide you with evidence of water and potential life that can or had been there on Mars. And then I will compare the sedimentology of Mars with sedimentology of Earth because I want to draw an analog between those two. Then all this discussion will lead us to the reconstruction of paleo environment and implication for habitability on Mars. And after that, after a very boring session or very, I don't know, interesting session, depending on your mood, I will just conclude my slide. And then I have, put some reference slides for further readings, for the pedantic ones that want to fact check whether the things I've said on the slides are right or wrong. So you can do that. Go ahead and do that. So, introduction. Without further ado, let's get into the introduction. So, in everything is an introduction, right? So, in this introduction, I will introduce you to concepts like planetary sedimentology, and I will also answer that burning question in your mind: why Mars? So, what is planetary sedimentology? You might ask. So, according to the Society of Planetary Sedimentologists, it is the study of how sedimentary processes work on other extraterrestrial bodies other than our Earth, that is, other planets, other moons, and etc. So we are all hailing from geological backgrounds over here, so I don't have to explain what the sedimentary processes are, but I have listed them over here if anybody is lacking or is, living under a rock. So you can check them out. So now a question might arise in your mind, like, how can we do that? How can we study those sedimentary processes over there, sedimentary processes, structure, etc. on, and other planets? So it is a valid question. Okay, so to answer that question, we cannot physically go over there and just we cannot just send geologists to Mars and or any other extraterrestrial planets and tell them to do some research, go do some research. No, we cannot do that. So we have to rely heavily on remote sensing data, and those are what those are acquired by either orbiters, that is satellites orbiting the planet, so or rovers. Those are vehicles that can move on their own or their program path, and they can actually send us high resolution surface images and also do some basic analysis on the surface of a planet. So we have to rely on those. And planetary sedimentology, why it is analogous to Earth's sedimentology, is the principles and the processes are almost same, but the overarching conditions like gravity, atmosphere, those are not same. So we have to do planetary sedimentology with a catch. That is, we have to keep in mind that factors like gravity, atmosphere, climate are very contrasting, very different on those planetary bodies. Now, coming to the question that is vexing your mind, that is annoying you, that is, that is um, aching your mind, and that is why is Mars special? So, to answer that question, I will first answer a question like why not Venus? Uh, Mars and Venus both are close to Earth, right? Both are terrestrial bodies and both can be studied. But remember, the surface temperature of Venus is about 460 degrees Celsius. So that is not geology we are going to be studying over there, but we will be studying barbecue over there, right? So 460 60 degrees Celsius is nothing, is not a joke, right, guys? And due to high igneous activities over there, high volcanic activities over there, frequent volcanic activities on Venus, most of the sedimentary processes are not that prevalent or even halted over there. So we cannot study sedimentary processes on a planet like Venus, right? And gaseous giants, there is no surface over there. How can we study, sedimentology where sedimentology isn't over there? So that kind of thing we have to keep in mind. So the points I've noted over here. Mars is the closest Earth-like planet. So it is the closest Earth-like planet, although it is half the size of Earth, almost half the size of Earth, but still it is Earth-like planet. But it has rich geological data sets. And why is that? Because of missions like, because of rovers, because of satellites, and because of this endeavor by NASA. So that is basically Curiosity rover, uh, Perseverance rover, Mars Reconnaissance Orbiter, and more, like there are Russian satellites also, there are Russian rovers there, but the Russian research papers they write in Russian, so I cannot actually refer from those. So I'm very sorry, but if someone of you actually know Russian, then go ahead and do that. And so these kind of rovers, these kind of orbiters, they actually target specific areas because Mars is a huge planet, even though it is 50%, 53% of the size of our Earth, but it is still a huge planet. And only a rover, only a satellite cannot cover the entire surface of the planet. So we have to rely on data sets acquired by many, many different rovers and many, many different orbiters that are specified to different specific locations. Like Curiosity rover, for example, is focused on the Gale crater. Perseverance rover is focused on the Zero crater. And Mars Reconnaissance Orbiter, it actually focuses, I think, on a fixed orbit. I don't know what the orbit is. So that is something. And studying, why study Mars? Now, I got to know why you can do planetary sedimentology on Mars, but why even study Mars? So that is a very ignorant question, by the way, but still, it is a good question. So studying Mars actually, so the core of Mars actually solidified and cooled down very early because of its smaller size. And so it actually gives us, evolution, like it actually gives us insight into the evolution of terrestrial planets, how climates shift from wet to dry. As we will see in the later slides, that Mars's climate actually shifted from a wetter condition to a very dry condition that is in the modern times, and whether the condition for life once existed beyond Earth or not. So whether there were microbial organisms on Mars or not, this is a question that has been uh, annoying us for a long time. So we will also delve deep into that in the later slides. Now, acknowledgement, right? So when I was in class 12th, I had to write projects on geography, history, and no, not in class 12, in class 10, 9, 10. So we had to write something called Kritagota, that is acknowledgement. So you have to basically acknowledge your gratitude towards the things that have helped you. Uh, Most of the time, I used to write the name of the teacher. So in the slide, in while making this slide, the data acquired by these four exploration devices, that is the Curiosity rover, Perseverance rover, Mars Reconnaissance Orbiter, and this Mars Odyssey orbiter, they actually helped me so much so that even though they are an inanimate object, I would like to, thank them very much for doing their work. So I actually named them the Big Four of Mars exploration. That is only for this slide, by the way. I don't know whether they are universally considered as the Big Four of Mars exploration, but their data, they have been very valuable for me, very insightful for me to make this slide while making this slide. So now coming to the main part of the presentation that I'm going to provide over here, that is the evidence of sedimentary processes. So sedimentary processes have to be there for me to study sedimentology on a planet, right? So the evidence of sedimentary processes on Mars can be acquired through the data observed by these orbiters and these rovers that we have sent. So first of all, I'm going to talk about the fluvial deposits that are on Mars. So what are fluvial deposits, you might ask? So fluvial deposits are nothing but the deposition by a river system, a river channel that occurs in a river channel due to the flowing water, due to the flowing water carrying the sediments and then depositing them when the flow rate is low. So what are the evidence of fluvial deposits on Mars, you might ask? So first of all, ancient river valleys, right? MRO, the thing I've mentioned in the past, that is the Mars Reconnaissance Orbiter, it actually reveals sinuous branching river channels across the surface of Mars. So many, many river channels, many sinuous river channels with tributaries and whole river systems are are there and can be found on the surface of Mars. So this actually shows that there were river flows, water flows on Mars. There were surface water on Mars. So I have included over here a picture taken by the MRO, and this is basically showing a main river and its tributary disconnecting over here in this point and then reconnecting somewhere out of this picture. Now coming to meandering patterns. So as we all know that meandering patterns is something that can be, only observed in a river that has been flowing for a long time. So basically it is evidence for sustained flow, not a short period flow or a short instantaneous flow, but a sustained flow that had been going on for a long time. So some valley networks in Mars actually resemble these meandering patterns. So I have shown a picture over here that has also been taken by that Mars Reconnaissance Orbiter or MRO. So this is the meandering pattern. As you can see, there are meanders forming over here. And to some extent, there are some horseshoe lakes over here that have been developed. So that means that Mars had sustained flow for a long period of time in its history. Now, coming to conglomerates, not any conglomerates, but rounded pebble conglomerates. So, Curiosity's mast. Do you know what a mast is? So, mast is basically the pillar or the pole on a ship that actually like supports the sails. So, Curiosity's mast cam, that is the camera on its mast, imaged conglomerate outcrops in the Gale crater with rounded pebbles. So, what is special about rounded pebbles? Rounded pebbles can only be abraded and transported by fluvial deposits or flowing water. Wind will not make rounded abrasions, rounded pebbles. Wind will only make angular pebbles. So, the presence of rounded pebble conglomerates actually shows us that there was flowing water channels on Mars, on the surface of Mars. And I've actually uh, pasted the pictures of the Gale crater where the conglomerates were found. So this is the conglomerate outcrop, and this is this one over here, the circled feature that is called something Hota. And sorry for my pronunciation, but the articles they do not have pronunciation, they do not have phonetics, the IPS system or anything like that, so that I can correct my pronunciation. They don't have any audio files so that I can listen to them. So you will have to actually listen to me obliterating the names of these words. So this Hota is a name of a rock that actually shows distinct rounded pebbles in the Gale crater. This photo was actually taken by the Curiosity rover, and I've actually given the scales over here. So these pictures are reference. You can trace back to their original article. Then comes FSRs. FSR was a thing that was very new to me when I was doing this research for this project. And FSRs. So what are FSRs? FSRs are nothing but fluvial sinuous ridges. So what are those? To be very honest with you, to be very concise, those are elevated features left behind from the Mars's watery past. So how do they form? Right? They form when sediment carrying water actually deposits its sediments, and the deposition, the mineral precipitation and the compaction actually forms a layer of deposition, a depositional layer that is, which is harder and more non-abrasive than the surrounding terrain. And when the river dries up and the wind and other agents start eating away the surface, the surrounding terrain, they get eaten away, they get eroded away, but the depositional layer, due to them being very hard, they remain over there. So when Mars's water actually disappeared, the aeolian erosions, they ate away the softer surrounding rock, right? They left behind the elevated FSRs behind. So these FSRs show that there was once a river carrying sediments was flowing along its path, right? So this is also an image by MRO. This is a high-rise image, basically high-resolution scientific imagery or something like that. So this has a pointy ridge, so it shows that it has been subjected to heavy erosion for a long time. Now coming to cross beddings and ripples, so this is something called a whale rock. This is also found by Curiosity rover. So this shows textbook crossbeds produced by ripples or dunes moving in water. So these actually like record the current direction during its deposition. So this was also actually taken by the mast cam. Catastrophic hydrology data from earlier missions like Pathfinder, the Sojourner River rover actually found out boulders conglomerate that were washed away and deposited by ancient floods that actually hint at episodic catastrophic hydrology. And these floods were so huge we should be thankful that we don't live on Mars, right? So the picture over here shows something named Mangala Valley. So it actually like this region has been subjected to intense episodes of flooding, and the cause of this flooding, what triggered these floods, are debated, but it is mostly speculated that it was some kind of volcanic activities or something like that, but it is controversial. Now we will move forward to the evidence of deltaic and lacustrine sediments. So what are lacustrine sediments, right? Deltaic, we can understand the delta sediments, but what are lacustrine sediments? Lacustrine sediments mean nothing but it is very simple. It is the lake sediments, right? So layered lake sediments. So the Mount Sharp or the Aeolis Mons that the Curiosity rover has been, climbing up for a long time, uh, in the past and also during the present, was actually built by sediments deposited in a large lake over tens of millions of years, right? So this actually shows finely laminated mudstones, flat lying strata in its, rocks, and it indicates that it had been deposited in a calm standing water environment, that is a lake environment. And this uh, layers of alternating lake, river, and wind deposits, I will actually like come back to this in this picture. So this is the picture of Mount Sharp. You can see the flat lying strata over here. Then we will come to the delta formations. So this picture, this second picture, this color picture over here, this is a picture of the Zezero crater. It is MRO, like Mars Reconnaissance Orbiter's most well-known pictures, and the color map over here actually shows us the different mineralogy. And this Jezero crater shows us a classic fan-shaped delta that formed when a river entered a lake. Okay, so this is something. Now, clay minerals, right? This is something that I had actually never thought about, like discovering on the surface of Mars, because I thought clay minerals was something, uh, I had a notion that clay minerals are something only specific to our Earth, but I have been wronged. So, clay minerals, right? Perseverance, which has been acting on the Jezero crater, has actually identified on the rims of this crater many clay bearing, that is phyllosilicate bearing rocks. So this is very exciting because it actually shows that. So one thing I forgot to mention is the surface of Mars is basically basaltic, right? So this basalt in had been exposed to liquid water for an extensive period of time, that indicates that there had been long lived water periods on Mars about 4 to 3 billion years ago. So that is something very interesting to me because I was dumbfounded by this statement over here. So I've shown the crocodilian plateau over here in Zezero crater where, you know, the Perseverance rover has found signatures of clay elements, clay minerals. Now coming to the aeolian deposits, that is the deposition by air. You will be very amazed to know that dune formation and aeolian deposits are still ongoing on the planet, the red planet. So, and the dunes and ripples formed over there are way, way higher and bigger in sizes compared to Earth due to Mars's low gravity. Mars has about 38% of the gravity we have on Earth, and Mars is way less denser atmosphere, so it actually exerts a very low pressure on the dunes. That is why they grow very large. And this Curiosity rover, again, on its way to Aeolis Mons, that is the Mount Sharp I've been talking about, actually found, vast dune fields like Nilipatera, Terra Sabea. I don't know whether I'm uh, obliterating their names or not, like annihilating their names, I think. But still, And one thing that did not actually cross my mind when I was making this slide is Terra Sylvia is the southernmost region of Mars. But this thing that actually strike my mind right now is why are the southernmost regions of any planet or any terrestrial bodies are very like enigmatic and very mysterious and very secretive. I don't know why. When the Chandrayaan 2 was going to Mars, I had actually heard that the south pole of moon is very enigmatic. It holds many secrets of the universe and something like that. And now, while talking about Mars, also the southernmost region is very enigmatic. I don't know why. I'll have to see. So curiosity actually provided us with this, first ground level look at active Mars dunes, that is the Bugnol Dune campaigns. The Bugnol Dune campaigns are illustrated over here. These are real photos taken by Curiosity's Mars Cam. Now, cross-bedded deposition, these are what? These are petrified windblown sand dunes. And these are typical, these can be found in the sandstones that um, you get on the Aeolis Mons or Mount Sharp. So this is a picture. Then Earth analogs, right? So as the processes are still ongoing on Mars, so we can draw analogs between the Earth deserts and the dunes on Mars, right? Dune fields on Mars. So basically, there is a place in California in USA called Death Valley, where Barkhan dunes uh, in the Mesquite Flats can be found, and those actually very closely resemble the Martian dunes. So studying these dunes on Earth actually help us interpret the Martian alien features, right? So I've actually pasted a picture over here, and if I'm allowed, I will just go to this link and show you the different kind of analogs they are. Like this is the this is Mars's Death Valley in California. You can see how like closely resembling these two are. You can draw many parallels over them, and these are the sand dunes I've been talking about. And this is, though the right one is a hypothetical one, but still they are very similar. So you can actually draw these kind of conclusions and these kind of things over here. So yeah, and sedimentary structures of research. So basically now we are moving on to the miscellaneous sedimentary structures of the that were not actually deposited actively, but were deposited due to some kind of secondary activities like evaporize. Like so, curiosity actually found out like sulfite-rich veins, sulfate-rich veins, and salt layers. So first of all, what is evaporite? Evaporite is nothing but rocks that formed rocks that are basically minerals that are basically like gypsum, jarosite, or halite, even maybe that actually formed due to the desiccation of a lake. That is the drying up of a lake. Because when the lake is drying up, the minerals in those, the salts in those, actually get very highly concentrated, and they form these, right? So curiosity actually found mud crack patterns and mineral salts and these kind of things that actually evidences that actually provides us evidence that these ponds went through overflow and drying cycles, like overflow then drying. So these evaporatic features actually mark desiccating environments, right? This is a mud crack feature that I found, that they have found uh, in Gale crater. It is called Old Soak. You can see the mud cracks are very well defined in this. So it indicates that there was a drying of a lake or something like that. So I will be moving on to the next slide, and that is secondary mineral growth. So by secondary mineral growth on Mars, we understand the hematite concretions and gypsum veins. I could not find any very good, hematite blueberries or the hematite concretion pictures. I should have actually included them from the Wikipedia at least, but I'm very sorry. But there are something called blueberries, blueberry hematite concretions. Look a lot like blueberries, so they are named hematite blueberries. on Mars, and you can actually see them. So gypsum veins, these are very much like, these show that there were multiple episodes of groundwater circulation, right? So sandstone formed due to some kind of fluvial activity or lake activity. Then there is secondary mineral growth, that is a hematite activity. Then you see over here, okay, by the way, this is a false color image. So the images are not what they are in actual form. They are false color images shown to us to actually interpret the structure or the mineralogy better. So this purple tone over here shows us hematite concretion. This bright and white vein over here, actually this linear feature over here corresponds to calcium sulfate mineral veins that indicate that there were multiple fluid circulation even post deposition, that are also indicative that there was long lived groundwater even after the lakes dried up. So that is something very interesting, because whether there is groundwater on whether there is groundwater under the surface of Mars still there is or not, this is a question that has been bothering the scientists for a long time, and they have found ice caps under, frozen water under the uh, ground surfaces, but they don't actually know whether they are still groundwater or not. So this is a question that you should ponder about, and tell me if you get to know something else. And so evidence of what? So from all these slides, we come to the conclusion that Mars definitely had liquid water on the surface as well as inside this, the below the surface, right? So from these conclusions, we can actually infer that Mars could have been, and it might have been actually been habitable at least by microbial organisms, right? For example, these mudstone mudstone flat over here I'm showing. Yes, uncle. एकदम ठिकै छु अङ्कल। म चाहिँ अङ्कल त्यो एउटा चाहिँ प्रेजेन्टेसन दिँदैछु। ओके अङ्कल। So this mud flats over here that are very enriched manganese dioxide actually implies that the lake water was actually oxygenated. It was rich in oxygen, and if it was rich in oxygen, at least it could have housed, microbial organisms. It actually could have been sufficient and supportive of microbial organism, the flourishment of microbial organisms. So that is something this respected gentleman over here at Los Alamos National Laboratory Space Science and Application Group, who is named Patrick Godze, he has actually been pondering. So this is a very good quote about the scientific approachment, scientific how scientists approach these things. So this thing actually interested me very much. So I have included this in the slide. You can read it if you like. And then comparison with Earth sedimentology, right? We had to come to this. So the sedimentary cycles on Mars and the sedimentary cycles on Earth are similar, yet they differ on some basic points like primary driving forces. The primary driving forces on Mars are actually not plate tectonics. As you know, on Earth, the plate tectonics provide the sediments during mountain building. Then they actually provide the deposition sites such as ocean basins through ocean floor spreading and things like that. But Mars actually, due to, as I have told you in past slides, that Mars's core actually cooled down very fast. So there were not very much, robust tectonism on Mars, even on early Mars. So sedimentary processes sediments are primarily produced by volcanism and things like, you know, volcanism and things like impact by asteroids, and this impact by asteroids also created craters like which acted as basins for these kind of sediments, which were deposited by fluvial and aeolian activities. So, as there was no robust tectonism, the recycling of sediments, the large scale recycling of sediments is very minimal on Mars. And due to the same reason, the preservability of ancient depositional environment is very high. And the contrasting things can be said about the sedimentary cycle on Earth. I don't think I have to elaborate on the sedimentary cycle of Earth because we are all aware. Now, the processes are almost same. I have actually like omitted the things like marine processes and glacial processes because there is a huge debate ongoing whether there was a uh, northernmost sea, on Mars or not, because there seems to be a feature. There seems to, appear something like there is a feature. This resembles something akin to a shoreline, but it is not continuous. So many scientists actually debate over that. So also, processes are almost same, but the overarching conditions you have to know that the overarching conditions are not very same because, as I told you, the gravity is about 38% of Earth. The atmosphere is about 0.6% of dense to that of Earth. So it means that wind can move sand. Furthermore, the water flow can move the sediments. Furthermore, because of less gravity and less atmospheric pressure. So as an example, the dunes on Mars they grow huge instead of like the ones on Earth that cannot grow that huge. So, what are the implications? All these discussions we have done so far leads us to these implications, right? What can we imply? What can we infer from this past climate? And what can we know about habitability? So, we can reconstruct the Mars's past like paleo environment, right? So by studying these kind of structures and all these things, the discussions we have had in the past slides, we can actually see that there was repeated cycles of repeated deposits on lake, like repeated lake deposits that actually imply that there was a periodically stable climate with liquid water on the surface available, right? And this transition from clay layers, okay, this transition from clay layers to calcium sulfate in the strata actually shows us that Mars had undergone through a wetter period to it actually shifted from a wetter period to a very dry period and is still in a very dry period to this day. And some of you might ask me, why did the surface water disappear, right? So as I've told you, the core actually solidified a lot faster, and due to the cooling down, due to the solidification of the core, the magnetosphere of Mars actually dissolved. It actually vanished. So due to that reason, the solar winds they actually stripped away all the atmosphere there was of the planet, like the red planet. So all the surface water it actually got, how should I say this, sublimated into space. So evaporated or sublimated into space, and that is how Mars actually basically lost most of its atmosphere and most of its hydrology, right? So hydrological reservoirs. We don't know about the groundwater, although some speculate that there might be some groundwater, like brine water, maybe. We don't know. So this is how Mars actually works, and then astrobiology. I have talked about this, whether life existed on Mars or not. And also, the sediment studies that we are doing right now will actually inform the future humans who will most probably go on Mars and explore. So we can actually tell them about the stable terrains and the past water reservoirs, these kind of things, and they can actually terraform. Have you guys, any of you, seen the movie Man of Steel? And if you have seen that movie, so Zod, basically the arch enemy of that movie, he actually come down. So he's the main antagonist, right? He's the main antagonist of Superman's Man of Steel. So he comes down to Earth and he tries to basically terraform Earth into Krypton so that the Kryptonites can find a home and those kind of things. Maybe we can do that in the future with Mars. So who knows? So I have actually tested the asteroid impacts, like I've told you. Most of the basins and most of the sediment formation was done by these asteroid impacts. So as you can see, it is spread throughout whole of the surface of the Mars, the red planet. So you can see this. Now coming to conclusion, right? Mars displays clear evidence of sedimentary geology analogous to Earth. As you can see, all are present fluvial, aeolian, everything is present. The planetary sedimentology actually like reveals that there was active hydrological and climatic cycles. So that is something very important to us, and we can actually infer and surmise that uh, the paleo environment and the shift of environment on Mars. So that is also very good. Now, the ongoing future missions, they will actually provide us more insight. They are actually providing us with more insight as I'm talking. These kind of things actually help us in unveiling the universe as well as the mysteries of the terrestrial planets and everything like that. And in to summarize my whole PPT, before that, I would like to say one thing. You guys are all now experts in planetary sedimentology on Mars, and don't be surprised if you get a call tomorrow asking you to come to NASA and work with them on Mars planetary missions. So who knows? And studying Martian sediments actually like bridges our understanding with both the sister planets, the blue planet and the red planet, and it actually answers a lot of curious questions we have about life and their history. So it is very nice. It is a very nice topic. Now, as I've told you, I've added all the references I've used in my slides. So everything I've referred, the pedantic ones, you can go and just fact check everything I've listed over here. And if you guys have any kind of questions, you can ask me. Apart from that, my slide for today is finished. So thank you for listening to me rambling on this planet, this red planet, and uh, I found it very interesting. I don't know about you guys, but I liked it very much. I like to research on these things and also talk about these things because this kind of things we are not taught in the syllabus. So sedimentology we were taught in our curriculum, and the earth sedimentology we were taught into our curriculum, and moving forward from earth and basically uh, what should I say, imposing the same principles of sedimentology on a different planet. This is something very interesting to me. I guess it was interesting to you because I've tried my hardest, tried rigorously, and through my rigorous research on this topic, I have actually wanted to convey the same interest to you guys. So thank you for listening. Thank you, and I appreciate your time. Thank you. And yeah, today I'm gonna conclude my presentation over here. Thank you for listening.